Alright, so essentially, I want to go over the principles of rate laws, principles of rate and reaction mechanisms. Okay, so essentially, before we begin, I have to break down the collision theory of reactions for you. Essentially, the collision theory of reactions, collision theory of reactions is relatively simple. It basically states that atoms and molecules are constantly like flying around at relatively high speeds, okay? And they're colliding all the time. They're like smashed into each other or whatever. But if you get certain molecules in a chemical reaction, what happens is that they collide in just the right way, with just the right orientation, and with sufficient speed. So two things, collision theory of reaction basically states that two things are necessary for a reaction to take place. Two things are necessary. A collision of the reacting species in exactly the right orientation. So, for example, let's say I have a molecule, right? Let's say this molecule is composed of several different atoms, and one of these atoms, one of these bonds is a little weaker than the rest, because the bond to this atom is not that strong, okay? So this orange bond is weaker than the rest. So if I have something, if I have another, like say, let's say I have another ion, let's say I have this red ion, okay? If it comes in like this, you get no reaction. You get no reaction because it's not hitting this with the right orientation. This hitting it here is just going to deflect and bounce off. It's not going to do anything to this. Or, if this hits right here, if it hits it straight on, well, see, the bond is here. So that's not really going to disrupt the bond too much. It's just kind of like compress it a little bit. But it's going to knock that, it's going to bounce right off, and you're going to get no reaction. However, if you get that ion coming in from over here, and it hits right here, this blindside attack from the back is likely to cause this bond to break, and you go from having no reaction to reaction. But it takes a pretty precise hit. It's not going to happen just hitting anywhere in the molecule. It's only going to happen if it hits exactly in the right orientation. Does that make sense? Okay, cool. So, the other thing, I'm sorry, should I have not erased that? Want me to redraw it? You're okay? Okay, cool, sorry. The other, the other factor that you have to consider is it needs sufficient energy. So there needs to be the collision happening, the collision must happen with sufficient energy, i.e. speed. If they don't collide hard enough, it will not be enough to cause the reaction to happen. It will not be enough to cause the trigger the breaking of bonds. So, going back to my little molecule that I was drawing earlier. And then we have that weak orange bond. And we have the rest of the molecules. Even if I have this red ion coming in and attacking, if it's too slow, it will not be enough to break this bond, and it'll just bounce off, and you'll get no reaction. Because it's just simply too slow, there's not enough energy to trigger the orange atom being kicked off. Does that make sense? So those are the two things required. So in actuality, the tenets of the collision theory of reactions basically state that all atoms and molecules are in constant motion, and this constant motion results in collisions between atoms and molecules. And then, when atoms and molecules collide in precisely the right orientation and with sufficient speed, chemical reactions occur. Those are the basic three tenets of it. But the main idea is this. The most important idea is this. They have to collide in exactly the right position, in exactly the right orientation, and there has to be sufficient speed. So now we have to think about, so what does that mean? What are the implications there? This whole chapter is about rate of reaction, right? We want to know what the rate of reaction is. So, what factors affect rate of reaction? Can you think of any?
Heat.
I'm sorry?
Heat.
Heat. Why would heat affect the rate of reaction?
Increase the molecule speed.
Increase the molecular speed.
Kinetic energy.
Yeah, because heat is a measure, remember, temperature is a measure of the average kinetic energy of particles, right? If you heat up a sample of matter, the molecules and atoms start moving much more quickly. And that means instead of being too slow, it's suddenly fast enough, more atoms and more molecules are colliding with more energy. And if also, not only are they colliding with more energy, but if you have a group of particles in a box, okay, and they're all like smacking around in there, if they suddenly increased, would they collide more often or less often? More often, right? So increase of speed does two things. So heat affects the rate of reaction by doing two things. It increases the speed and therefore the number of collisions, and it increases the energy of those collisions. So if roughly, just because of probability and statistics, if maybe 0.2% of all collisions resulted in a successful chemical reaction, if you increase the speed and the energy, you'll increase the percent of successful reactions to maybe like 0.5, because more of the correct collisions will have sufficient energy. But you're also going to increase the number of collisions. So whereas if it was 0.2 times a billion before, and it's 0.5 times a billion, because 0.5 times, you know, so if you, let's say if it was initially 0.2%, and I'm just making up this random number, times, we'll say 10 to the 25th, or 10 to the 23rd. 0.2 times 10 to the 23rd collisions, that's going to give you, a certain amount. It's going to give you 2 times 10 to the 22nd successful chemical reactions. But if more atoms have if more of the collisions have the sufficient energy they need to react, then that increases the percentage of successful collisions. A higher percentage of the collisions will be successful because they'll have sufficient energy. However, it also increases the number of collisions. So instead of 10 to the 23rd collisions, maybe you have like 10 to the 25th collisions because they're moving so much more quickly. So now you have 5 times 10 to the 24th successful reactions. So heat actually affects both of these in a positive way. What's another factor that affects rate of reaction?
You could slow it down with taking away the heat, so like freezing it.
Well, yeah, so once that's related to heat though, right? So factors that affect rate of reaction, one of the big ones is heat. What is another one?
Concentration.
Concentration. So which of these two conditions does concentration affect? Did somebody say it? And I didn't hear it? Because I'm a little deaf.
The second.
The second, yeah. Well, actually no, because increasing the concentration only increases the number of particles, right? Is that going to affect the energy of those particles? No, the temperature is still the same, right? So which factor will it affect?
First.
It's going to affect the number of collisions. So that'll be more likely to be the first one. It's not going to change the energy, but it will increase the number of correct collisions simply because it'll increase the total number of collisions. In that case, it's the same. You may still have the same 0.2% success rate because the energy is the same, so it's the same percentage of collisions that is successfully reacting. However, because you have so many more collisions, because you have so many more particles, you're going to have an increased number of successful reactions. Does that make sense? Factors that affect rate. So, heat, concentration, what else?
Presence of a catalyst.
Presence of a catalyst. What will a catalyst do?
Speeds up the reaction, but is not consumed.
What'd you say?
Speeds up the reaction, but isn't consumed.
It does, but which one of these factors does a catalyst
Number 2.
help? The second one or the first one?
The second one. The second.
It's actually the first one. Because if you think about a model of an enzyme, have you all taken biology? Has anybody taken biology? Okay. In biology, an enzyme is a biological catalyst. So an enzyme is shaped in such a way as to hold a very specific type of substrate. Okay? So if you got a molecule that has this shape, it's going to fit in the enzyme. Okay? And there will be certain attractive particles in here, attractive ions and other things like that will draw this in, so to speak. There'll be certain forces that will attract it. But this piece slips into the enzyme, and then you get a chemical reaction that occurs. Well, essentially, the best analogy I can think of is, let's say, a terrible analogy. Let's say you're trying to beat up somebody who's bigger and stronger than you are, right? So you get like 3 or 4 people to hold the guy down, and then you can beat him up easily, right? You try to do it yourself, you're probably going to get whooped. So same thing with an enzyme. An enzyme is this group of bigger, stronger people, or a group of bigger people to help you hold down this bully or whatever, and then it can break up the molecule and cause whatever to happen, right? So it ensures that the collision happens in the right orientation, because the enzyme is holding it into place and forcing it to be in the right position. Does that make sense? So that's kind of like what a catalyst does. Although there are different types of catalysts, not all of them follow this kind of lock and key mechanism. Some things just give the reaction a new pathway to proceed. It creates kind of a new mechanism where there are certain sub-reactions that are easier that happen first before the final product is formed. But what it comes down to is usually it either changes the reaction entirely to give it different steps, or it simply holds it in the right orientation. And that's what a catalyst does. Alright, and then the last but not least, and this one's not as obvious, but it is the surface area. Or at least it's obvious, but it's not something you necessarily would think of. Surface area. So, for example, if you tried to light metal on fire, you may not be very successful, right? You have some, like a bar of iron and you try to light it on fire. It might char a little bit on the outside. It's not really going to start bursting into flames or anything, right? But if you shaved that down to powder and you lit the iron powder on fire, it would flare. It would break. So, the truth is, surface area is a huge deal. Rate of reaction is much bigger if there's more surface area. And what that comes down to, once again, is increasing the number of collisions. If you have more exposed surface area, there's more collisions and the reactions happen faster. Does that make sense? Okay. So now probably what you are more waiting for is the actual problem solving part, am I right? So, effectively, as you already know, as you probably already know, if you have a reaction A plus B goes to form C plus D, and it has coefficient little a, little b, little c, and little d. Actually, I'm not going to use little a, little b. I'm actually going to use real numbers because otherwise it's kind of confusing. Let's say 2a plus 3b equals c plus 4d. Okay. Let's say we have this chemical reaction. The rate of the reaction can be given in terms of any single one of these because essentially for every 2a that reacts, 3b is going to react, right? And for every 3b that reacts, 1c is going to be produced. So I can actually give the rate of the reaction in terms of any one of these. The thing is, if I simply write the change in the concentration of A over the change in T, is that going to be the same as the change in C over the change of T? Are those two rates going to be the same? They're not, right? Because the coefficient of A is 2 and the coefficient of C is 1. So they have different coefficients. So the rate of change of A is not the same as the rate of change of C. So what chemists decided to do to solve that problem is we give the rate of reaction in terms of the fraction of the coefficient. Okay? So that the rate of reaction is the same no matter which substance we calculate it from, we take 1 over the coefficient times delta A over delta T. Okay? Now here's the thing though. Another thing that chemists thought about is like, well, we don't want to think about it as a negative rate. Like, you can't have a negative rate. Right? You can't have negative 1 moles per liter reacting per second. That doesn't make any sense, right? So, like, well, we have to have positive rate of reaction. You can't have a negative rate of reaction. There can be a negative change in how much A is left because A is going to go away over time, right? It's being reacted. So the fact that the change in A over change in time actually is negative, the amount of concentration of A is decreasing. To make the rate of the reaction positive, we have to slap a negative in front of it. Okay. Does that make sense? So that is the rate of reaction with respect to A. Now I'm going to do one weird little thing here. I'm going to pull this parentheses over, and I'm going to put the negative inside the parentheses. And then put the 1/2 out here. Why am I going to do that? That's for me to know and you to find out. No, I'm just kidding. This quantity here actually has a special name. The negative delta A over delta T. This is referred to as the rate of disappearance. And I forgot how to spell disappear. Disappearance. I feel like there should be two S's there, but I don't know if that's true. This one? Okay. Rate of I'm not an English major. Rate of disappearance of A. So the rate of disappearance of A is, like I said, all rates must be given in terms of a positive number. That's why we have the little negative on the inside. But this quantity here is referred to as the rate of disappearance. So sometimes in a problem, it'll say the rate of disappearance of oxygen is 3.7 moles per liter, or molarity per second, rather. 3.7 molarity per second. And then it'll ask you, what is the rate of formation of nitrogen? And so you have to be able to relate those two. But to relate those two, you have to understand that the rate of disappearance is actually this quantity right here. Okay, so next, if we were to write the rate in terms of B, what would we write? How would we write the rate of reaction in terms of B? 1 over 3.
The negative one.
Negative sign.
Change of B over T.
Delta concentration of B over delta T. Yeah. That's it. Does that make sense? And what about the rate of C?
1 over 1.
What would be the rate of reaction with respect to C?
1 over 1.
1 over 1? Of course, if 1 over 1 is just 1, right? So you wouldn't actually even need to write that one, right? And then what? What'd you say?
Delta concentration C. Delta concentration C.
Yeah, delta concentration C over delta T, right? Negative sign?
No.
No. Why?
Rate of appearance.
Yeah, because the rate has to be positive and the product is going to increase over time, right? These are going down because they're reactants, but the product is going to increase. All right, and then what about the last one?
1 over 4.
1 over 4.
Delta.
Delta concentration of D over delta T. All right, absolutely. Now, in this case, this likewise would be a rate of disappearance. This would be a rate of disappearance of B. And this here would be a rate of appearance. This would be a rate of appearance of D. So, rate is always given as a positive number. If you have a rate of disappearance of a particular substance, it's represented by this thing here. It does not include the fraction of the coefficient. So those just a couple things to keep in mind. All right, let's look at some problems. It says, if the concentration of C2H4 is decreasing at a rate of 0.37 molarity per second, what are the rates of changes in concentration of CO2 and H2O? Okay, so in this particular case, it gives you this reaction. It gives you the reaction C2H4 plus 3O2 goes to form 2CO2 plus 2H2O. Right? So, now it says C2H4 is decreasing at a rate of 0.37 molarity per second. What is that? What is that 0.37 molarity per second? It's a rate of
Disappearance.
disappearance. It's the rate of disappearance. So what might help us here, since we have to compare this to CO2 and H2O, right? We have to compare this to CO2 and H2O. I might want to write out the rate of reaction in terms of each of these just to compare them. So I can say that the rate of this reaction is equal to negative delta C2H4 over delta T, which is equal to, if I have to compare this to CO2 and H2O, I'm not going to worry about the oxygen. I'm going to skip over to the other side. 1/2 times delta CO2 over delta T, which is also equal to 1/2 delta H2O concentration over delta T. Now, one thing you'll probably notice here is that whatever the rate of appearance of CO2 is, what is it in comparison with the rate of appearance of H2O? How do they compare? How do these two rates of appearances compare? Is one going to be bigger than the other? They're going to be the same, right? Yeah, they're going to be the same. They have the same coefficient, so they're going to be the same rate. So really, if I can solve for one of these, I can solve for both. Now, the rate of appearance it gives me, remember this whole thing here is the rate of disappearance. I don't actually have to calculate delta T. That whole thing is the rate of disappearance, which is actually given to me. So this is actually 0.37 molarity per second. And that's equal to, and what am I looking for? I'm looking for the change in concentrations. So I'm looking for the change in concentrations, or the rates of change in concentration. That's the rate of appearance. The rate of change in concentration is the rate of appearance. So I'm actually looking for this. So if I wanted to assign a variable to this, let's call it x. This is basically 1/2 x is equal to this. By knowing your definitions, you take something that actually looks pretty darn complicated, right? And make it into something extremely simple. Make sense? Okay, so then, what is x in this case? What is the rate of appearance of CO2? What do you think?
Multiply that by 2.
Yeah. What was that giving?
0.74.
Yeah, there you go. Good deal. So now, while this works with concentration, it also works with pressure, because sometimes it's change in concentration, sometimes it's change in pressure. It depends on whether or not we're measuring the rate in terms of change in concentration or change in pressure. Because if you remember from the gas laws unit of the last time, or whatever you took, I was going to say last semester, but whenever you took Chem 1, it may not have been last semester, right? The gas laws unit specifically mentioned that the pressure of a gas, if the volume is the same, the pressure of the gas is proportional to the number of moles, right? If you have more pressure, that represents a proportional increase in the number of moles. For example, if you remember PV equals nRT, does that look familiar to you? If the temperature is constant and the volume is constant, so you're comparing one pressure to another pressure, this is constant and this is constant, essentially comparing two gas samples, since R is a constant, R is constant for any ideal gas, PV over NT should always add up this, give you the same number. So P1V1 over N1T1 is equal to P2V2 over N2T2. Now, if the temperature and the volume are constant, if they're not changing, then they kind of factor out of this equation, right? And that gives you this relationship here. And even though this doesn't entirely look like it, this is a direct relationship. Because what this is saying essentially is that if you increase the pressure here, you're going to, if you increase the pressure from P1 to P2, so in other words, if P2 is twice P1, then the moles have to be twice as well. Otherwise the fraction's not equal. If you double this one, then this one also has to be doubled. If you halve this one also has to be halved. So moles and pressure are proportional. So instead of using concentration, we can also use pressure to measure the rate of reaction, because pressure is directly proportional to the number of particles. That makes sense? Have I lost you? You're still with me? Awesome. I know I'm running through this a little bit fast, although probably not as fast as I should if I want to get through it all, but yeah. So, here we go. Let's go ahead and take, well actually let me ask you this. There are some probably more important things that we probably should take a look at first. Do you want to go ahead and skip the second one since we already kind of know how to do the changing? Okay, let's do that. Let's go to the second practice problem. It says reaction between ethyl bromide and hydroxide ion and ethyl alcohol at 330 Kelvin is given as follows. Is first order in ethyl bromide and second order in hydroxide ion. So it's first order in ethyl bromide, second order in hydroxide ion. And so what is the value of the rate constant and what are the units of the rate constant? So, and it says when C2H5Br is 0.0477 molar and OH minus is 0.100 molar, the rate of disappearance of ethyl bromide is 1.7 times 10 to the negative 7 molarity per second. Now if we look at this reaction, C2H5Br, and it says it's an alcohol as opposed to being aqueous, if you're wondering what that ALC is. And then you have the C2H5OH, ethyl alcohol product, and bromine, Br minus, here. Okay, so here's the deal. If I want the rate of reaction, because it actually, remember, I want the rate of reaction. And actually, let me step back for just a second. So, there's the rate expressions, right? The rate expressions are essentially when you do that whole, let's say if I want the rate of reaction in terms of this, is a rate equation or rate expression. Rate equation or rate expression. And that would be given as negative delta C2 H5 Br over delta T, right? That's a rate equation or rate expression. That's not the rate law. There's another thing that we use in expressing rates called the rate law. And the rate law is rate is equal to some rate constant K. We don't know what it is, but some rate constant K times the concentration of one reactant, C2H5Br, to some power which we don't know, to the m power, times the concentration of the other reactant, OH minus, to the n power. In many ways, the rate law is more useful. The rate law tells us something about the mechanism of the reaction. How is this reaction happening? What steps are happening? So, for example, in this reaction, according to the collision theory of reaction, is it that this ethyl bromide is smashing into the OH minus, and that just makes the reaction happen in one step? Or is it that ethyl bromide smashes into ethyl bromide and forms a little subproduct, and then the OH minus comes in and attacks that subproduct, and then forms the final product? Or is it the OH minus smashes into another OH minus and causes a little subreaction, and then that, or is it the OH minus reacts with something else? So is the ethanol there part of a catalyst? There's a lot of different possibilities for how this reaction could play out. And the rate law gives us insight as to what those possibilities are. It tells us which one of those possibilities is correct. That's why this is so useful. This is just what you use in the lab to measure the concentration, a change in concentration or a change in time. You can measure what the concentration is at a given point in time, and then you can measure the change in concentration over the change in time. But that doesn't tell you about how the reaction is happening. This does. So, in this problem, it says it is first order in ethyl bromide and second order in hydroxide. So, a first order in ethyl bromide means that this exponent here is 1. A second order in hydroxide means that this is 2. So what does that mean? What does that mean when you have these exponents 1 and 2? Well, usually what it means is that there are, in the rate determining step, in the step that determines the rate of the reaction, the slowest step of the reaction, you have 2 molecules of OH minus smashing into 1 molecule of ethyl bromide. And that's why the rate law is dependent, that's why the rate is dependent upon the concentrations with these powers. Because you have 2 of these that need to smash into 1 of these to make the products. Does that make sense? So, now in this case it wants to know what the value of the rate constant is. That's what it's asking us. But before we can know the value of the rate constant, K, we need to know this, this, and this, right? Does it give us the concentration of ethyl bromide?
Yes.
Yes.
Yeah.
And the concentration of ethyl bromide is what?
0.0477.
Yeah, 0.0477. That's molarity per second. And what is the concentration of hydroxide?
0.1.
Okay. 0.1. Squared, right? That's molarity per second as well. Oh, actually, no, it's just molarity, sorry. That's just concentration, it's just molarity. My bad. Okay. And then here's, now do we know what the rate of reaction is? Well, technically it only gives us the rate of disappearance, right? But in this case, the rate of disappearance is the rate of reaction, right? However, if there was a number in front of here, we would have to take that into account and use that to solve for the rate of reaction. Does that make sense? So, in this case, the rate of disappearance is the rate of reaction, so we can plug that in as 1.7 times 10 to the negative 7 molarity per second. So now we have to not only solve for the value of the number of rate, the number value of rate constant, we also have to solve for the units. So, if we calculate this, what's going to be molarity times molarity squared? Molarity cubed. So I have K times essentially some, whatever this number is, actually I know what it is, it's essentially going to be 0.000, yep, 477 molarity cubed, if you multiply that, right? And then I'm going to set that equal to this. Well, that's equal to the 0.7 times 10 to the negative 7 molarity per second. And then I'm going to divide both sides by essentially this 4.7 times 10 to the negative 4th molarity cubed. 4.7 times 10 to the negative 4th molarity cubed. That's going to cancel this, and I'll get my K value. If you have your calculators out, go ahead and calculate that. If you don't have them out, get them out. It would only be 2 sig figs because you only got 2 here. So 3.6
Yeah.
times 10 to the negative 4. And what would the unit be? From molarity over seconds divided by molarity to the third, what would the unit be? So molarity, this is molarity to the first, right? Molarity per second, that's molarity to the first. When you divide exponents, you subtract them, right? 1 minus 3 is, so this is going to be molarity to the negative 2. And of course, since seconds is in the bottom to begin with, you could write it as seconds to the negative 1. Alternatively, if you wanted to, you could also write this as 3.6 times 10 to the negative 4, 1 over molarity squared seconds. Does that make sense? So it's loud up here, and then close the door again, go. Get some extra air before I do. Okay. Pretty good. Awesome. Now it said, how would the rate of disappearance of ethyl bromide change if the solution were diluted by adding an equal volume of pure ethyl alcohol to the solution? What would adding pure ethyl alcohol to the solution do to the concentrations of each of these? Specifically adding an equal volume. Was it okay that I erased that? I guess I can't really undo it now, right? Sorry. I need to be more circumspect. Alright. I added an equal volume of ethyl alcohol. What would that do to the concentrations here?
Make them stronger.
I'm sorry?
Make them stronger.
If you add alcohol to the solution, would you have a higher concentration of this? No, the concentration would be less, right? Just like you add water to a solution, the concentration drops, right? So if you had an equal, so if you doubled the volume of water, it would have the concentration, right? If you doubled the volume of ethyl alcohol, made the solution essentially twice as much, double the volume of the solution, that would mean these concentrations were half, right? Half as much. So if I have this and I have that, what would the rate be? So in this case, what you can do is you can say, well, let's say if I had, say, X here originally, and if I had X here originally, then the rate would be equal to Kx cubed, right? Does that make sense? But if I have both concentrations, so that the new rate, I'm going to call this rate prime, or actually I'll just call it rate 2. Then, if rate 2 is equal to k times 1/2 x times 1/2 x squared, what's that going to give me? 1 over 8. So this is going to be 1 over 8 kx cubed. So if I doubled if I doubled the volume here, if I added an equal volume of ethyl bromide, what would happen to the rate? Got the math all set up for you? What happens to the rate?
Go down by 1.
It goes down to 1/8 of its original rate. So if the rate was 8.0 molarity per second, it would go down to 1.0 molarity per second. It goes down to 1/8 of its original. So that's a dramatic drop from from having the concentration, I dropped the rate to 1/8 of what its original one was. Make sense? Cool. Let's see what else we got here. Now that you know what rate law is and rate equation, so the rate equation, rate expression, and rate law, now that we know both of these and the difference between them, we can look at how we do some experiments. And you'll be doing a lab like this pretty soon, although not exactly like this. Alright, this following set of rate data was collected for the reaction of nitrogen monoxide with oxygen in the following equation. 2NO plus O2, 2NO plus O2 goes to form 2NO2. Okay. So it says, what is the rate law for this reaction? So in a case like this, you have to understand that rate law is given only in terms of the reactants. And there's no way to predict the rate law based on this. Because here's the thing. Let me paint a little picture for you. You could have an NO react with NO to form NO2 plus, you could have NO to form NO2 plus O. Okay? And that could be the first step of the reaction. You could then have the oxygen from there reacting with another NO to form NO2. Oh wait, that's not gonna that's not gonna work. Oh, NO2 plus N. There we go. NO2 plus N. There we go. I have to laugh at myself when I make mistakes like that. Okay, so then I can have another N react with another O2 to form NO2. Okay? Now, if you add this together, it will give you the same overall reaction, right? Let's say the reaction happened in these two steps. If this is the fast, or if this is a slow step, and this is the fast step, you might see that the rate of the reaction, the rate law, would not even include oxygen. The rate law would simply be KNO squared. Because the rate law is based on the rate, the elementary rate step of the slowest step of the mechanism. So the rate law is based on the slowest step of the different steps that make up the overall reaction. So if that's the slow step, that's the one that determines how fast the reaction goes, and therefore the rate law would be this. Notice this does not look like this. But we can't know for certain that this is what the rate mechanism is. But the point is, you can't look at an equation and know what the rate law is. You can't predict the rate law from the equation. There's just no way. So you actually have to do an experiment. And that's what this experiment is going to show. Okay. So what I do is I set up, with this rate data, this experiment, I measured the rates when I have different concentrations, right? See the little table? So what I'm going to do is I'm going to write a generic rate law. Since I don't know what the rate law is, but I do know that the rate law has the possibility to contain both reactants, but rate law does not contain products, right? It's just focused on the reactants, because based on the collision theory of reactions. So NO can be, let's say, to the M power, because I don't know what the power is, times O2 to the N power, right? So rate is equal to K NO to the M power times O2 to the N power. Now if I want to figure out, I want to figure out the rate law, which means I want to figure out what the exponents are. So here's how I can set that up. I can look at the trial data, and I can find two, because right now there's just way too many unknowns, right? I can find two sets of data, two experiments, where one of the concentrations is kept constant and the other one is changed. So which two experiments do you want to start with? 2 and 3. Okay, that's good. 2 and 3. So as a general rule, I like to start with the one, I like to have the one that's on top be the one with the higher rate. So I'm going to put trial 2 on top. So I'm going to say trial 2 and I'm going to write the rate for trial 2, which actually, I know what the rate for trial 2 is, right? It says 1.13 times 10 to the negative 1. 1.13 times 10 to the negative 1 molarity per second. And that's equal to K, which I don't know, times the concentration of NO for trial 2, which is 0.0252 molarity to the M power, times the concentration for oxygen, which is 0.0250. 0.0250 to the N power. Okay? So, here I have 3 unknown variables. No way to solve for the exponents with this. So then I set up another set of rate data with trial 3. In trial 3, I put in my rate, it's 5.64 times 10 to the negative 2 molarity per second. And that's equal to K times the concentration of NO for trial 3, which is 0.0252 molarity to the M power, times the concentration for O2, which is 0.0125 molarity to the N power. So now that I have these two expressions, I'm going to go ahead and divide them. I'm going to divide this by this. And that's the smartest thing I can do mathematically, because that allows me to cancel out what? What does that allow me to cancel out? The 0.0252, right? It doesn't matter what M is going to be the same number for both, so 0.025 to the M is going to be 0.025 to the M. They're going to be equal. So this cancels out. What else cancels out? K. K cancels out. So I just cut out 2 of my 3 variables that I did not know, and now I can focus on the 1 that's remaining, and I can solve for it. So that gives me 0.0250 to the N over 0.0125 to the N. And if I divide this by this, what do I get? Then I can pull the exponent out, right?
2.
I get 2. So this is actually basically going to be 2 to the N power. And then on this side, I take 1.13 times 10 to the first, 10 to the negative first, divided by this, and what does that give me? 2, right? So 2 to what power gives you 2? 1. So N is equal to 1. So that means the order of reaction with respect to oxygen is 1. It's first order with respect to oxygen. Did that make sense? So then I do the same thing. I do the same thing with 2 other trials where oxygen is kept constant. So that means I can use trials 1 and 3, right? So I'll set up that, and the higher concentration there is for trial 3. So I'm going to go ahead and erase this bottom part. Actually, does anybody need to copy it? Okay, I'm going to go ahead and erase the whole thing then. I'm going to set up another comparison, and I will do trial 3 and trial 1. So trial 3 I'm going to put on top because it has a higher rate. And you don't have to, it doesn't really matter if you put trial 3 on top or trial 1 on top. But I just like to work with whole numbers instead of fractions, so that's why I just put the higher rate on top. It just makes it easier for me to do the calculations in my head. Alright, so trial 3, it's going to be 5.64 times 10 to the negative 2, right? And that's equal to K times the concentration of NO from trial 3, which is 0.0252 molarity to the M power, times the concentration of O2, which is 0.0125. And we know it's to the first power. I'm still going to put N, just because, I don't know, I don't care. It's going to cancel out anyway. And trial 1, the rate is 1.41 times 10 to the negative 2 is equal to K times the concentration of NO, which happens to be 0.0126, to the M power times 0.0125, 0.0125 to the N power, right? So I'll divide these then. And so with this, I can clearly see that my oxygen now cancels out, and my K is still going to cancel out. And so now I can go ahead and do the final part and solve for M. And 0.0252 divided by 0.0126 is going to be what? 2, right? Yeah, 2 to the M. So 2 to the M power is equal to,
4.
what's 5.64 divided by 1.41?
4.
4. So 2 to the M is equal to 4. So what's M?
2.
M has to be 2. 2 squared is 4. So M is equal to 2. So this is second order with respect to NO. So that whole proposal that I made last time, at the beginning of the problem, where I showed you those different rate mechanisms, yeah, that was wrong. Because I had my rate law being NO squared, right? So that means that mechanism must not be right. Now you see the value of the experimental data and these predictions. Now that I know what the rate law is, I can predict what the mechanism would be. It's definitely not that other one that I was thinking about. So now I write the rate law of the reaction as a very nice bold color. So the rate is therefore equal to K times the concentration of NO squared times the concentration of O2 to the first power. This is my rate law. Second order in NO, first order in oxygen. Now, from this, if I wanted to, I could now finally calculate what the value of the rate constant is, right? Because I have all this rate data, I could just plug in one set of rate data, and with the appropriate numbers of 2 and 1 there, and I could solve for K, couldn't I? So, I can solve for the value of the rate constant, and answer the relating the questions that follow. So that's basically how you use rate data to solve for the rate law of a reaction. And I think that's as far as we're going to get today, but are there any questions or anything to cover? Well, you all have a great day. Thank you for coming.